Hey nerds! Nearly 60 years ago, Star Trek promised us warp drive, the ability to zip across the galaxy at faster than light speeds, visiting new worlds, seeking out new civilizations. The USS Enterprise could reach other star systems in days or weeks instead of centuries. Kirk could have adventures on multiple planets, meeting many, many women in a single season. I think he fell in love every single episode. The crew could explore the galaxy and still make it home for tea. And without warp drive, Star Trek would just be like Starship, the incredibly long, boring journey where everyone dies of old age before anything interesting happens. It's arguably one of the most important pieces of technology in science fiction history because it makes interstellar stories possible. Now, to be clear, Star Trek didn't invent this idea. Come on. We already had science fiction jump drives from Asimov, which are the best. We had Dune's Highliners and many, many pulp sci-fi stories talking about spaceships that could bring you across the galaxy. But Star Trek brought it to the masses. It's probably most people's first encounter with science fiction. So warp drive is their kind of glory or icon of faster than light travel in fiction. So the big question though, where is it? Why aren't we zipping around the galaxy? Is warp drive just impossible fantasy? Is there any real physics behind it that we might someday harness? Well, the answer is complicated, because warp drive kind of sits in this strange space where the mathematics says it could work, but reality says, like, no. It's theoretically possible in the same way that lifting the moon with your bare hands is theoretically possible. Actually, I don't even know if that is. But the laws of physics don't explicitly forbid it, but good luck actually doing it. That's the problem. Today we're going to deep dive into the physics of warp drive, why Einstein says you can't go faster than light, how Alcubierre found a sort of a loophole, why that loophole doesn't actually help, and why even if we solved all of the physics problems, causality itself would break. Before we get into it, I'm Abby, I'm a physicist, I'm finishing up my PhD at the University of Oxford, and I make sci-fi science videos on the side for, you know, lols. But if you like what I'm doing, then you should subscribe and follow along. And if you really like what I'm doing, then you should consider joining the Nerd Club on Patreon. Anyway, let's get into warp drive. Let's start with the problem warp drive is trying to solve, and that is the speed limit of the universe. Einstein's special relativity, which was published back in 1905, fundamentally changed how we understand space and time. And one of its most important results is that nothing with mass can reach the speed of light. Now, this isn't just some sort of practical limitation, it's built into the structure of space-time itself. You see, as you accelerate, your kinetic energy increases. That's just basic physics. But in relativity, energy and mass are equivalent through the very famous E equals mc squared. So as you accelerate, that added energy contributes to your total energy, and it makes you increasingly harder to push. Your inertia skyrockets as your speed approaches the speed of light. Inertia like inertia. If you know, you know. Physics used to say the particle gets heavier, but that's not quite right. It doesn't gain mass, it just takes more and more energy to keep speeding it up. Now, at 90% the speed of light, your total energy would be about 2.3 times your rest mass energy. At 99%, it's about 7 times, and at 99.9%, it's about 22 times. As you approach light speed, the required energy climbs without limit. Each extra 9 in your velocity costs exponentially more energy. But you'd never reach 100%. No amount of fuel, not even all the energy accessible to us in the universe, will ever let you reach light speed. Like I said, this isn't an engineering problem where better engines would help. The universe fundamentally just doesn't work that way. Now, there's another effect that makes faster than light travel even more problematic, and that's time dilation. You see, as you accelerate towards light speed, time slows down for you relative to everyone else. At 86% light speed, time runs at half the normal rate for you. At 99.5% light speed, time will slow down by a factor of 10. So you would experience 1 hour while 10 hours passes for someone stationary. This effect becomes infinite as you approach light speed. And if you could somehow reach exactly light speed, which you can't, time would stop entirely for you. You'd basically experience no time passing at all between departure and arrival, no matter how far you traveled. So from your perspective, the journey would just be instantaneous. But it would still take centuries, millennia from everyone else's perspective. Civilizations would rise and fall before you completed the journey. For interstellar travel to work, for storytelling, or for any practical purposes, you need faster than light travel. But Einstein says you can't have it. No. Unless there's a loophole. So, Einstein's relativity says you can't move faster than light through space, but it doesn't say that space itself can't move. General relativity, Einstein's theory of gravity, published in 1915, describes gravity as the curvature of space-time caused by mass and energy. Massive objects bend the fabric of space-time around them. You see, space-time isn't a fixed stage where events happen. It's dynamic. Near massive objects, it curves. Around rotating black holes, it would twist, and this bending isn't limited by the speed of light. During the first fraction of a second after the Big Bang, space-time itself expanded faster than light in a period called cosmic inflation. Even now, distant galaxies are receding from us faster than light because the space between us is expanding. Now, these galaxies, they're not actually moving at like a velocity that's faster than light. It's the space between them that is stretching and growing. And this space can expand or contract at any rate, and that's the difference. In 1994, Miguel Alcubierre, a physicist doing his PhD at Cardiff University, was studying general relativity, and he was also watching Star Trek like we all were. He started thinking about whether you could use relativity to create something like warp drive. Now, we do have to interject here for a second just to say that the original idea of warp drive in Star Trek in the 60s was centered around subspace. The ship would shift into this extra-dimensional region where the laws of physics would operate differently, allowing them to travel at warp factors, which were speeds faster than the speed of light. And that's basically what warp was, and what the bubble was the bubble that allowed them to move into subspace. Now, subspace is not a real thing in physics, and it does seem that more recently or more modern versions of Star Trek have adopted the Alcubierre Drive and, the use of dilithium crystals and antimatter reactors as a way to describe what is actually happening. So that's why we're going to focus on the Alcubierre Drive version of warp and not subspace. Now, his approach was pretty straightforward here. He was saying, what if you compressed space-time in front of a ship and then expanded it behind it? Because then the ship wouldn't move through space faster than light. Instead, space itself would just move around it, carrying the ship along. Inside this warp bubble, the ship would be stationary relative to its local space-time, but the bubble itself would move by contracting the space ahead and expanding it behind. So the ship kind of surfs like a wave of moving space-time. Now, Alcubierre worked through the maths and he published his results in a paper called The Warp Drive Hyper-Fast Travel Within General Relativity. Now, the equations were a valid solution to Einstein's field equations. Physicists genuinely found this really interesting, but the practical problems were pretty obvious from the start. So what made the paper valuable wasn't that anyone thought that we could build a warp drive. It was that it was this new demonstration that general relativity allows some pretty strange solutions. So, in this configuration, you could theoretically travel faster than light without violating relativity. You're not moving through space faster than light, you're manipulating space itself. And general relativity doesn't forbid that. But it absolutely doesn't work in practice. So for nearly 2 decades after Alcubierre's paper, warp drive remained a theoretical curiosity. It was interesting mathematics, but obviously impractical. Then, in 2012, Harold Sonny White at NASA's Johnson Space Center published a paper suggesting that maybe, just maybe, we could reduce the energy requirements. You see, Alcubierre's original calculations showed that you'd need negative mass energy equivalent to the mass of Jupiter. White suggested that by changing the bubble's geometry, making it a toroidal configuration instead of a spherical one, the energy might drop by like orders of magnitude, but under some very optimistic assumptions. He suggested you could reduce it to something more comparable to like a spacecraft's mass for a small bubble. Still impossible with our current technology, but conceptually it was way less absurd than like the Jupiter mass of Alcubierre's paper. There was a lot of buzz in the news and the media. There were headlines everywhere saying that NASA was working on faster than light warp drive. The internet kind of lost its mind a little bit. They thought we'd have starships by 2050 before Zeph from Cochrane. People were booking their tickets to Alpha Centauri. The future was here. The physics community, though, I got excited for about 48 hours, because you see, then people actually started doing some more detailed calculations and checking the assumptions that White made. Looking at his other work as well, now White had been promoting the EM drive, which was a device that supposedly produced thrust without propellant by bouncing microwaves around in a closed cavity. Now multiple labs tried to replicate it and it just didn't work. The supposed thrust was a measurement error. And his warp drive paper, like I said, it made some optimistic assumptions about the energy requirements. And when the other physicists checked the maths more carefully, the energy needs were still astronomical. And crucially though, even if you could reduce the energy requirements, you still had all the other problems. Problems that don't go away no matter how you optimize the geometry. Now, White's paper is no longer prominently featured on NASA's website. His research program didn't actually really lead anywhere. But for a brief moment, warp drive seemed possible, close, maybe, seemed like it was maybe just an engineering challenge after all. It isn't, it isn't. We still, no matter what, have the exotic matter problem. You see, one of the most fundamental problems with Alcubierre's warp drive is that it requires exotic matter. This is matter with a negative energy density, effectively behaving as if it had negative mass. And I know what you're thinking here, right? You're thinking, well, quantum mechanics allows negative energy densities. We've seen them in the lab. It's the Casimir effect. Everyone always loves to bring up the Casimir effect. And this is real, absolutely. You take 2 uncharged conducting plates and you place them very close together in a vacuum, so like nanometers apart, billionths of a meter, and then quantum fluctuations in the vacuum create a measurable attractive force between the plates. The energy density between the plates is slightly negative compared to the surrounding vacuum. It's a genuine quantum effect that has been measured. But there's kind of a critical distinction here, because the Casimir effect is a temporary energy fluctuation in a very specific configuration. It's not matter with a negative mass. It's a quantum vacuum effect that produces negative energy density under very particular conditions. So, while negative energy densities can exist in quantum mechanics, that's not the same as having matter with negative mass that you can collect, that you can store, and then use to power a warp drive. Now, Harold White's paper suggested that you could reduce the energy requirements by changing the warp bubble's geometry, so like I said, making it toroidal instead of spherical, and he claimed that this could bring this negative energy density requirement down to something closer to Voyager's mass. But like I said, his calculations made some optimistic assumptions, and those assumptions were about how the geometry would affect the stress energy distribution. The reality is that the geometry changes don't actually reduce the exotic matter requirements needed for this configuration. You still need a negative mass energy equivalent to Jupiter's mass, which is about 2 × 10⁻27 kilograms. So this is the scale problem that kills any hope of using the Casimir effect. Because the Casimir effect produces forces that are measured in like pico to nanonewtons. And it's done between plates that are separated by nanometers. The negative energy density is minuscule. And we're talking about 30 orders of magnitude difference between what we've observed in the Casimir effect and what we'd need for a warp drive. That's not just scaling. That's the difference between lifting a grain of sand with your finger and lifting the moon with your finger. If you could scale up the Casimir effect linearly, which you can't, you'd need conducting plates the size of the solar system, separated by meters, and you'd need to maintain quantum coherence across the entire distance in the vacuum of space for extended periods of time. We can barely maintain quantum coherence across millimeters for milliseconds in carefully controlled lab conditions. And again, that's assuming that you could scale the Casimir effect, which you probably can't, because the effect depends on the quantum vacuum fluctuations between the plates at specific separations. If you make the plates bigger or you make them further apart, the effect doesn't scale up. It changes in really complex ways. So trying to scale up the Casimir effect to be able to use it for a warp drive, very not going to happen. We would need to have actual exotic matter. We would need matter that has a negative mass. Now, negative mass would have some really, really weird properties. It would repel normal matter gravitationally. So if you pushed it, it would accelerate like towards you, not away. And most physicists think that large amounts of negative mass are probably impossible. I mean, yeah, they might violate fundamental principles like energy conditions that keep the universe stable and causal. So warp drive needs something that doesn't exist or something that does exist in quantities 30 orders of magnitude beyond anything that we've ever possibly observed, with properties that might be fundamentally impossible in the universe. But let's just say that we solved it. Let's say we solved it. Let's say we found or we created exotic matter in Jupiter mass quantities. We would still have some more problems, you guys. We need to talk about radiation. As you travel through space in your warp bubble, you're plowing through the interstellar medium. That's gas, dust, cosmic rays, photons from distant stars. Normal space isn't empty. Now, there's about 1 hydrogen atom per cubic centimeter in interstellar space. That sounds sparse, but when you're moving at effective faster than light speeds, you're going to encounter a lot of atoms. The ship isn't literally plowing through gas, but the warp front interacts with ambient particles and photons. Now, approaching radiation is going to be severely blue shifted, and it will pile up on the leading edge of the bubble. So every low energy photon you encounter becomes a gamma ray. Every hydrogen atom you meet becomes a relativistic particle with enormous kinetic energy. This radiation builds up on the front of your bubble as you travel, and the longer you travel, the more it accumulates. It's trapped there by the warped space-time at the boundary of the bubble itself. So when you then drop out of warp, all that energy has to go somewhere. and it would explode outwards in a cone in front of your ship. A directed gamma ray burst, basically. One of the most energetic phenomena in the universe. It's a pretty cool weapon. Your arrival would be announced by accidentally sterilizing everything in front of you. So imagine that, like the Enterprise dropping out of warp near Earth. The gamma ray burst would hit the planet before anyone even knew that the ship had arrived. The atmosphere would be stripped away. All life on the surface would die instantly from radiation exposure. We come in peace, immediately followed by accidentally committing planetary genocide. It's first and last contact all in one. Now, this is what the models predict, and multiple physicists have worked through the calculations. The radiation buildup is unavoidable if you're moving through space at effective faster than light speeds or having space move around you. So you'd need some way to either prevent the buildup or safely discharge the energy, and neither seems possible with known physics. But beyond the radiation hazard, there's also the practical problem of actually getting to where you want to go. Let's talk about navigation. Now, science fiction makes interstellar navigation look super easy. You plot a course, you engage your warp drive, you arrive at your destination. What could possibly go wrong? Well, everything. Everything could go wrong because everything in space is constantly moving. Earth orbits the sun at 30 kilometers per second. The sun orbits the galaxy at about 200 kilometers per second. The galaxy itself is moving relative to other galaxies at hundreds of kilometers per second as well. There's no fixed reference points. To plot a safe course at warp speed, you'd need to know the exact position and trajectory of every object along your path. Because if you drop out of warp inside something solid, well, that's going to be the end of the journey, right? The galaxy contains hundreds of billions of stars, trillions of planets and asteroids, countless comets. Interstellar space isn't empty. Like we said, it's full of gas, clouds, dust, rogue planets, brown dwarfs. Most of this is dark. You can't see it from a distance. You only detect it when you're relatively close to it. The only way to map a route safely would be to travel it first at slower speeds, observing everything and tracking all of the orbital mechanics. Then you could use warp drive. But that kind of defeats the purpose, doesn't it? Because if you need to travel at normal speeds first to make the map, why bother with warp drive? And by the time you've mapped the route anyway and traveled it once, everything will have shifted and moved. Planets move in their orbits, asteroids drift, your map's going to be out of date. You need the map to use warp drive safely, but you kind of need warp drive to make the map quick enough in order to make the map relevant to use warp drive. It's chicken and egg situation. Now, Isaac Asimov actually kind of addresses this in Foundation series with his jump drives. They use instantaneous transitions between points in space, but they still need to very, very carefully plot all of the courses and to calculate the jumps that they're going to use in order to account for all the gravitational fields along the path. It's some of my favorite scenes in his books, particularly I think it's Foundation's Edge or Foundation and Earth and Stars Like Dust as well, I think. Yeah, the Stars Like Dust. They're great stories that he really goes into the jump drive technology or the idea behind the navigation issue with jump drives. Whew, I let myself go off track, so I lost the ability to speak. So, coming back to Star Trek, who completely ignores the navigation issue other than just saying, plot a course and raise the shields. But it's okay, because it's, you know, it's Star Trek sci-fi, we're fine with it. We're cool with it. But, even if you could navigate safely, there is still a fundamental constraint on where you can use warp drive. The space-time distortion needed for an Alcubierre bubble is enormous, like enormous. You're bending the fabric of space-time around your ship on a massive scale. Near planets or stars, space-time is already curved by their gravity. So adding a warp bubble's distortion on top of that existing curvature creates instabilities. The two distortions interfere with each other in ways that could tear the bubble apart or cause it to collapse unpredictably. You could only safely engage warp drive in deep interstellar space, asymptotically flat space-time, far from any significant gravitational sources, which means you'd need conventional propulsion to get out of a solar system first. Engage warp in the empty space between the stars, then disengage well away from your destination and fly the last portion again at normal speeds. Because think about it, if you still need to travel at impulse to get far enough away from the gravity of the sun, you're still going to be traveling for like a year or so before you can actually hit warp. Now, you might be thinking, but Abby, come on, man, they're all practical problems, things that could be solved. You know, at the end of the day, Alcubierre still is a solution to the field equations, so I'm just going to go with it. Well, according to what I have said so far, the maths says warp drives could work. Except it doesn't, not really. The Alcubierre solution is a legitimate mathematical solution of Einstein's field equations. That is absolutely true. But it's not one that fits physically reasonable energy conditions. And we're not just talking about energy amounts. Now we're actually talking about fundamental rules that keep the universe working properly. These are the weak energy condition, the dominant energy condition, and the null energy condition. These are the basic constraints that ensure that energy behaves normally in general relativity. So the null energy condition, that's the one that we're going to talk about here, says that energy density can't be negative along light-like directions. This is because negative energy creates universe-breaking physics, causality violations, time travel paradoxes. It always comes back to it, you guys. Now, every known form of matter mostly satisfies these rules. Yes, quantum effects can bend them locally, but never enough to do what warp drive needs. The geometry that creates the warp effect requires you to violate these conditions, and we've known this since the 1990s. Now, there was a period back in 2021 where a series of papers appeared to find ways around some of the energy requirements, but all of these papers, just like Alcubierre's original work, only look at one type of observer, one reference frame. But energy conditions have to hold for all observers in space-time, all reference frames. And when you check them all, the violations reappear. And it's not fixable. The space-time geometry that makes warp drive work is the same geometry that violates the rules. So even if you solved energy requirement amounts, exotic matter, radiation, gravity, and navigation, you would still be trying to create something that breaks fundamental physics. And the final kicker, I hinted at a second ago, faster than light travels always violates causality, no matter what, no matter how you achieve it, whether it's through warp drive, wormholes, quantum tunneling, whatever it is. Moving faster than light creates situations where cause and effect break down. This isn't about the specific mechanism. It's about the structure of space-time itself. Now, in special relativity, different observers moving at different speeds disagree about whether two events happen simultaneously. And that's fine for slower than light travel. Everyone still agrees, though, on the order of cause and effect, which event caused which. But with faster than light travel, you can construct scenarios where different observers disagree about the order of events that are causally connected. You could send information into your own past. This means you could receive a message from your future self. You could prevent yourself from sending that message, but then if you don't send it, you don't receive it, so you don't prevent yourself from sending the message. It just keeps going round and round and round. It's not a thought experiment. It's a genuine consequence of combining faster than light travel with relativity. Now, the universe appears, for all intents and purposes, to run on causality. Every effect has a cause. Cause precedes effect. Time flows forward, faster than light travel breaks all of that. Most physicists think causality is more fundamental than relativity. If something violates causality, it's probably impossible, even if the mathematics technically say it could be allowed. So warp drive is mathematically allowed by general relativity, but it violates causality. And causality is probably non-negotiable.
Scotty, I can't change the laws of physics.
So where does that leave us? Well, as I said, warp drive is mathematically possible, technically, kinda. The Alcubierre metric is a valid solution to Einstein's field equations. The equations don't forbid it, but just because you find a solution in the maths doesn't mean you have everything you need to build it for reals. And we have to face reality. We need a form of matter that doesn't exist, a way to safely remove the radiation buildup, a way to navigate an unmapped galaxy, and a way to not break causality. It's not an engineering challenge. It's asking the universe to change, and nobody likes change, you guys. Star Trek's warp drive is brilliant science fiction. Like, it really is. Come on. It opens up the galaxy for storytelling. We have had season upon season that we have loved of different versions of this show. It lets characters travel between stars and have adventures, but we can't have it. Not in this universe with these laws of physics. At least not unless we're fundamentally wrong about how, like, reality works, which is always possible. You know, science has been wrong before, sure. But right now, all of our evidence suggests that warp drive is impossible. The speed of light isn't just a speed limit, it's the speed at which cause and effect propagates. It's built into the structure of space-time, and we can't change that no matter how much we want to explore the galaxy. The stars are very, very far away, and they're probably staying that way. So that's why we can't have warp drive, not because we haven't figured out the engineering yet, but because the universe fundamentally just doesn't work that way. The universe says no. What do you think, though? Is there some other loophole we're missing here? Some way around these problems? I don't think so, but let me know in the comments. I'm still trying to be hopeful. I can't help it. I'm always going to want to be hopeful about this. But that's it for me for this month. That is Warp Drive. I will, of course, be releasing some shorts about this episode where I might talk about a few different topics in a little bit more in depth. So keep an eye out for that. And thank you for watching. If you enjoyed this, then subscribe. And for Patreon this month, what I think I'm going to do is I'm going to look at those 2021 papers, the Eric Lentz soliton solution, and there was a couple of more papers that came out around the same time. And then there's a really good paper as well in 2022 that kind of explains why these solutions are not valid and why they all still break these energy conditions because of this lack of looking at all observers, where when you're just looking at one reference frame, you can kind of make things happen if you want them to. So yeah, go and check that out. Join the Nerd Club if you are interested. But for now, thanks for hanging out with me, and let me know what you would like me to talk about next month. Thanks for watching. Stay nerdy.